Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to finish up our lecture on applications of aqueous equilibrii, and we've made it to the last and final objective titled titrations and buffers. To begin this objective, we're going to first focus on buffers. A buffer solution is essential in chemistry because it helps maintain a stable pH even when small amounts of acid or base are added. Buffers resist changes in pH by using a combination of a weak acid and its conjugate base or a weak base and its conjugate acid. And this balance between acidic and basic components allows the solution to absorb added hydrogen ions or added hydroxide ions without significant changes to the pH. Now, to understand how a buffer works, let's first look at what happens when you add a strong acid to a buffer solution. For example, if hydronium ions from a strong acid are introduced to a buffer solution, then they are quickly neutralized by the conjugate base of the weak acid that's present in that buffer. The reaction shifts to produce more of the weak acid, and that keeps the pH relatively stable. On the other hand, if a strong base like hydroxide is added, the weak acid in the buffer donates a proton to neutralize the base, and this creates more of the conjugate base and water. These reactions demonstrate the dual role of buffers in neutralizing both added acids and added bases, and it ensures that the pH remains stable. The stability comes from the equilibrium between the weak acid and its conjugate base, or vice versa, which can shift to accommodate changes in the concentrations of hydronium ions or hydroxide ions. With that being said, there are three primary ways to prepare a buffer. The first involves mixing a weak acid or weak base with its corresponding salt. So for example, combining acetic acid with sodium acetate forms a buffer because the acetic acid acts as the weak acid and acetate ions serve as the conjugate base. This combination ensures that the solution has both components needed to neutralize the added acids or bases effectively. Another way to create a buffer is by mixing a weak acid with a strong base, but in a controlled ratio. Before I show you an example, I want to take some time to explain BCA tables. A BCA table is used when a reaction is best described as going to completion rather than as an equilibrium. BCA stands for before reaction, change, and after reaction. When a reaction goes to completion, we solve it using the techniques we learned for solving stoichiometry problems in General Chemistry 1. Although a BCA table is similar to an ICE table, they're not exactly the same. Stoichiometry problems, which can be solved using a BCA table, differ in two important ways from equilibrium problems, which are solved using an ICE table. First, we have to use moles when we're solving stoichiometry problems rather than concentration. Second, since the reaction goes to completion, the amount of change listed on the change line of the BCA table is determined by the amount of limiting reactant. Keeping that in mind, let's take a solution that initially contains 0.1 moles of a weak acid. And to this solution, we're going to add 0.05 moles of potassium hydroxide. The hydroxide ions from potassium hydroxide are going to react with half of the weak acid to produce the conjugate base. And this is going to result in equal concentrations of both the weak acid and its conjugate base, and this mixture forms a buffer. Now this is demonstrated in this BCA table. So we have 0.1 moles of our weak acid, and we have 0.05 moles of potassium hydroxide. Now, in this reaction, we see that the mole-to-mole ratio of reactants is 1:1. So the limiting reactant is going to be the reactant with the fewest number of moles, which is our potassium hydroxide. All of the potassium hydroxide is going to react with our weak acid, and what we're left with is 0.05 moles of our weak acid, and we have formed 0.05 moles of our conjugate base. So again, this is another way to create a buffer, and it's by mixing a weak acid with a strong base. Now, what's the last way to prepare a buffer solution? Buffers can also be prepared by mixing a weak base with approximately half as much strong acid. For example, if a solution contains 0.1 moles of a weak base and 0.05 moles of hydronium ions are added, the strong acid converts half of the base into its conjugate acid. This leaves us with equal concentrations of the weak base and its conjugate acid, creating a buffer. And this BCA table demonstrates this reaction. So again, we start with 0.1 moles of our weak base and 0.05 moles of hydronium ions. In this reaction, the mole-to-mole ratio of reactants is 1:1. So the limiting reactant is the reactant with the fewest numbers of moles, which is hydronium ions here. After the reaction, we're left with 0.05 moles of our weak base and 0.05 moles of its conjugate acid, forming a buffer that can resist changes in pH. So once again, we have three primary ways to prepare buffer solutions. The first involves mixing a weak acid or a weak base with its corresponding salt. The second way is by mixing a weak acid with approximately half as much strong base. And the third way is by mixing a weak base with approximately half as much strong acid. Let's go ahead and jump into a practice problem now. This problem says, which of the following mixtures would form a buffer? Let's start with part A. Part A says we have 100 milliliters of 0.1 molar nitric acid mixed with 100 milliliters of 0.1 molar sodium nitrate. Now, any solution containing a weak acid and its weak conjugate base will act as a buffer. Therefore, to determine if this mixture will form a buffer, we have to consider all of the species present in solution. Remember that nitric acid is a strong acid, and when a strong acid ionizes an aqueous solution, it completely dissociates. For this reaction, it's going to dissociate into hydronium ions and nitrate ions. In addition, sodium nitrate is a soluble salt, so it's also going to dissociate and it's going to give us sodium and nitrate ions. When nitric acid and sodium nitrate are mixed, we're going to have the following species in solution. We're going to have water, we're going to have hydronium ions, we're going to have sodium cations and nitrate anions. Sodium and nitrate ions behave as spectator ions in acid-base reactions. So this mixture actually doesn't contain a weak acid or a weak base, and that means it's not a buffer. Actually, the mixture of a strong acid or a strong base with one of its salts doesn't form a buffer. So for part A, this mixture is not a buffer. Let's apply the same logic to part B. In part B, we have 100 milliliters of 0.1 molar hydrogen cyanide mixed with 100 milliliters of 0.1 molar potassium cyanide. In this solution, hydrogen cyanide is a weak acid, and potassium cyanide is a soluble salt. A soluble salt that is going to completely dissociate in solution. So from this salt, we're going to have potassium and cyanide ions. And actually, in solution, the major components in this mixture are going to be water, the weak acid, hydrogen cyanide, potassium cations, and cyanide anions. This solution is a buffer because it contains the weak acid, hydrogen cyanide, and its weak conjugate base, cyanide ions. And so for part B, this mixture is a buffer. Let's tackle part C. Part C says we have 100 milliliters of 0.1 molar hydrogen cyanide mixed with 50 milliliters of 0.1 molar potassium hydroxide. At first glance, it might appear that this mixture would not form a buffer since it initially contains a weak acid and a strong base. However, as soon as these two solutions are mixed, the weak acid reacts with the strong base in this manner. We have our hydrogen cyanide plus our hydroxide ions. They give us cyanide ions and water. So that means we have to consider all of the species that are present after the reaction between hydrogen cyanide and hydroxide ions. And actually, for any weak monoprotic acid that is neutral, like hydrogen cyanide, we can actually just write it as HA to denote weak acid. And we can write this as hydroxide ions, and that gives us our weak conjugate base plus water. And this shorthand equation is useful because it describes the reaction of any weak monoprotic acid with any strong base. When an acid-base reaction has either a strong acid or a strong base on the reactant side, it goes to completion, hence why we wrote a one-way arrow here. And this equation is written with a one-way arrow because this is not an equilibrium process. And this is going to have consequences in the way that we solve this problem for two reasons. First, this is going to be a stoichiometry problem. Stoichiometry problems have to be solved using moles or millimoles rather than concentration. And second, stoichiometry problems are always limiting reactant problems. And all of that is going to influence the way we answer this problem. Now, the first thing we want to do is we want to figure out the moles or millimoles of our reactants present here. We're given volume information and we're given the concentration, so we should be able to work backwards because molarity is equal to number of moles of solute divided by liter of solution. Now here specifically, we're not given liters, we're given milliliters. So if we were to use milliliters without converting it to liters, our answer for number of moles is going to have units of millimole, which is perfectly fine as long as we are consistent with our units when we are figuring out our moles of weak acid and hydroxide ions. So if we're solving for the numerator here, number of moles or millimoles, we want to isolate that variable. We're going to rearrange this equation. Millimoles is going to be equal to molarity multiplied by our volume in milliliters. And we're writing it this way because we're given the volume in milliliters. That means that when we calculate molarity multiplied by milliliters, our answer for moles is actually going to be in units of millimole. Keeping that in mind, let's figure out our initial mole for our weak acid and for our hydroxide ions. So the number of millimoles for our weak acid, hydrogen cyanide, this is going to be equal to the molarity, 0.1, multiplied by 100 milliliters, which is our volume. This gives us 10 millimoles of our weak acid. We'll do the same for our hydroxide ions. We're going to figure out the number of millimoles for hydroxide ions. This is equal to the concentration, 0.1 molar, multiplied by our volume, 50 milliliters. This gives us 5 millimoles of hydroxide ions. Wonderful. Now we're going to use these values to set up our BCA table. So I'm going to do some erasing here so we have room. We have our general form of our reaction written here. To the side, we're going to write BCA. We're starting with 10 millimoles of our weak acid and 5 of our hydroxide ions. In this reaction, we notice that there is a mole-to-mole ratio between the reactants that is equal to 1-to-1 ratio. And that means that the reactant with the fewest number of moles, or millimoles in this case, is the limiting reactant. For our problem, that's going to be the hydroxide ions, because we have less millimoles of that, and all 5 millimoles of hydroxide ions is going to react with the weak acid to form approximately 5 millimoles of our weak conjugate base. So then in our after reaction line, we're going to have 5 millimoles of our weak acid left, none of our hydroxide ions, and we would have formed 5 millimoles of our weak conjugate base. Now these two values for our weak acid and for our conjugate base are equal. And that means that what we have here is a buffer. This mixture is a buffer. And with that, we've answered this problem, and we can move into our next topic. Our next topic is the Henderson-Hasselbalch equation. And this equation is a powerful tool that allows us to calculate the pH of a buffer solution and understand how a buffer resists changes in pH. A buffer solution maintains a relatively stable pH by containing a weak acid and its conjugate base, or a weak base and its conjugate acid. And when small amounts of acid or base are added to a buffer, the weak acid or base present neutralizes them, and that prevents large changes in pH. The Henderson-Hasselbalch equation helps quantify this stability by relating the pH of the buffer to the concentrations of the weak acid and its conjugate base. This equation can be expressed mathematically like so. In this expression, pKa is the negative logarithm of the acid dissociation constant Ka, which tells us how easily the weak acid donates protons. And then this ratio here represents the relationship between the concentration of the conjugate base and the concentration of the weak acid in the buffer. This ratio reflects the balance between the two components of the buffer, and that is really crucial in maintaining pH stability. So when the concentration of the conjugate base increases relative to the weak acid, then the pH of the buffer rises. On the other hand, when the weak acid becomes more prevalent, then the pH decreases. To derive the Henderson-Hasselbalch equation, we start with the equilibrium expression for the dissociation of a weak acid in water. For this reaction, we can then write the equilibrium constant, Ka, and that is going to be equal to the concentration of the products raised to their respective stoichiometric coefficients, divided by the concentration of the reactants raised to their respective stoichiometric coefficients, not including liquids or solids. Then from there, we can rearrange the equation to solve for the hydronium ion concentration. And by rearranging, we get the following expression you see here. Then we can take the logarithm of both sides, and that gives us equation 3. This log can then be distributed to both of these variables. And from there, we're also going to multiply both sides by -1. This gets us negative log of the hydronium ion concentration on the left side of this equation. This is equal to pH. This is the definition of pH. Then we have a negative log of Ka. This is the definition for pKa. And then our final term here is a negative log of our concentration of weak acid to conjugate base. If we flip the numerator and denominator, then this negative sign changes to a positive sign, which is done for this Henderson-Hasselbalch equation, and that is our final form. This version of the equation allows us to directly relate the pH of the buffer to the concentrations of the weak acid and its conjugate base. A critical feature of this equation is that when the concentrations of the acid and base are equal, then this ratio we see right here is going to be equal to 1. And the logarithm of 1 is 0. So the pH at this point is going to be equal to the pKa. This condition, where the concentration of the weak acid is equal to that of the conjugate base, represents the point where the buffer is most effective at resisting changes in pH, and this is often referred to as the half equivalence point in titrations. A similar relationship applies to buffers made with a weak base and its conjugate acid. For these systems, we use POH instead of pH, and the equation becomes POH is equal to pKb plus the log of our concentration of our weak base and its conjugate acid. Here, pKb represents the negative logarithm of the base dissociation constant Kb, and this ratio right here demonstrates the relationship between the concentration of the weak base and its conjugate acid. Since pH and POH are related by the equation pH plus POH is equal to 14, we can easily convert between them when necessary, depending on the system we are analyzing. Now, the Henderson-Hasselbalch equation is particularly useful for practical calculations. It simplifies the process of determining how a buffer's pH will change when small amounts of acid or base are added. In some cases, we can further simplify calculations by using moles instead of concentrations. Since concentration is defined as moles divided by the volume, and the volume remains constant during many buffer preparations, the ratio of the concentrations can be written as the ratio of moles, and this is especially helpful when preparing buffers by mixing known amounts of a weak acid and its conjugate base, or vice versa. Another important concept that's tied to the Henderson-Hasselbalch equation is the buffer range and buffering capacity. The buffer range refers to the range of pH values over which the buffer can effectively resist changes in pH. This range is typically within 1 pH unit above or below the pKa of the weak acid. So for example, if the pKa of a weak acid is 4.8, the buffer will be most effective between a pH of 3.8 and 5.8. Outside of this range, the concentrations of either the acid or the base become too low to effectively neutralize added acids or bases, and this can weaken the buffer's ability to stabilize the pH. Now, the buffering capacity refers to the amount of acid or base that a buffer can neutralize before the pH begins to change significantly. A buffer works best when the concentrations of the weak acid and its conjugate base are roughly equal. If one component is much more concentrated than the other, then the buffer becomes less effective because it can only neutralize a limited amount of added acid or base before the system is overwhelmed. With that being said, let's jump into a practice problem. This problem says, determine the pH of a buffer formed by mixing 50 milliliters of 0.1 molar hydrofluoric acid with 40 milliliters of 0.15 molar sodium fluoride. And here we're given the Ka value for hydrofluoric acid. It's equal to 6.8 times 10 to the negative 4. Now for this problem, the Henderson-Hasselbalch equation can be used to determine the pH of any buffer. Here, this is the concentration of the weak base in the mixture, and this is the concentration of the weak acid in the mixture. Notice that the concentrations given in this problem represent the concentrations of the acid and base before being mixed. Therefore, we can't use these values, 0.1 molar hydrofluoric acid or 0.15 molar sodium fluoride, in this equation. But one advantage of the Henderson-Hasselbalch equation is that it allows us to express the amount of weak base and weak acid in terms of either concentration, moles, or millimoles. We talked about this earlier, and we're going to be taking advantage of this to figure out what to plug into this part of our equation. Now, what we're given here is molarity, and we're given volume in milliliters. So to figure out the number of millimoles, we can multiply molarity by the number of milliliters. We saw this equation in a previous problem in this video. We're going to use it again here to figure out the number of millimoles for our base and for our acid. So for the number of millimoles of our base, this is going to be equal to 0.150 molar, all right, multiplied by our volume, which is 40 milliliters. This is all given to us in the problem here. We're given 40 milliliters of 0.15 molar sodium fluoride. If we plug this into a calculator, we're going to get 6 millimoles for our base. We're going to do the same thing for our acid now. What is the number of millimoles for our acid? This is going to be our hydrofluoric acid. This is equal to molarity, 0.1, multiplied by our volume, which is 50 milliliters. Again, all of these values given to us in the problem. Plug it into the calculator, we're going to get 5 millimoles of our acid. Perfect. Now that we have that, we can start to plug things into our equation. One thing to point out is we're not directly given the pKa, but we know that pKa is equal to the negative log of Ka, and we're given the Ka value. So we will be rewriting this pKa term as negative log of Ka. That means that our pH can be calculated in the following way. It is going to be the negative log of Ka, 6.8 times 10 to the negative 4, plus the log of our moles of base, 6 millimoles, divided by the number of millimoles of our acid, which is 5 millimoles. If we plug this into a calculator, we're going to get that our pH is equal to 3.25. And with that, we've solved this problem. And now we can move into discussing titrations. Titration is a fundamental lab technique that's used to determine the concentration of an unknown solution by reacting it with a solution of known concentration. This method is crucial for quantitative analysis in chemistry, particularly for analyzing acid-base reactions and redox reactions, to name a few examples. In a typical titration, the solution with unknown concentration is known as the analyte, and this is placed in a flask. To this solution, a titrant is gradually added from a burette, and a titrant is a solution of known concentration. The key to titration is monitoring the reaction between the titrant and the analyte until the equivalence point is reached. This point signifies that the amount of titrant added is exactly enough to completely react with the analyte meaning that the moles of titrant equal the moles of analyte based on the stoichiometry of the reaction. Now, at the equivalence point, the number of equivalents of acid and base are equal. And this fact allows us to calculate the unknown concentration of the analyte through this equation. Here, N represents normality, V represents volume. To calculate normality, this is going to be equal to the equivalence of solute divided by the volume of solution in liters. Equivalents represent the reactive capacity of a substance, and this is often based on the number of moles of reactive units, like protons, electrons, hydrogen or hydroxide ions, etc., that participate in a reaction. So again, the formula to calculate normality is equivalence of solute divided by volume of solution in liters. During a titration, the use of a pH meter or an indicator helps in identifying that equivalence point. A pH meter is an electronic device that measures the pH of the solution, and it allows us to monitor the change in pH as the titrant is added. An indicator, on the other hand, is a substance that changes color at or near the equivalence point, and the choice of indicator really depends on the expected pH at the equivalence point. Now, it's also important to distinguish between the equivalence point and the endpoint in titration. The equivalence point is the theoretical point where the number of moles of titrant added equals the number of moles of analyte present, indicating a complete reaction. The endpoint, however, is the point at which the indicator changes color, signaling that the titration should stop. Now, ideally, the endpoint should coincide with the equivalence point, but there can be slight differences, which can be minimized by choosing an appropriate indicator. To summarize, titration is a precise method used to determine the concentration of an unknown solution by reacting it with a known solution. Now, acid-base titrations, they can be performed for different combinations of strong and weak acids and bases. The most useful titrations involve at least one strong species, either a strong acid or a strong base, and this is because strong acids and bases fully dissociate in water, leading to more clear and more abrupt changes in pH that accurately indicate the equivalence point. Weak acid, weak base titrations, although possible, are rarely performed due to their inherent limitations. The pH curve for a titration between a weak acid and a weak base tends to lack the sharp inflection that's typically seen at the equivalence point in titrations involving strong species. And this makes it difficult to precisely identify the equivalence point, which can lead to less accurate results. Nevertheless, we're going to cover different titration types, starting with strong acid with a strong base. To understand the dynamics of titrating a strong acid with a strong base, let's dive into an example where we titrate 10 milliliters of a 0.1 normal solution of hydrochloric acid with a 0.1 normal solution of sodium hydroxide. By plotting the pH of the solution against the volume of sodium hydroxide added, we obtain a titration curve that reveals important aspects of the titration process. At the beginning, when only small amounts of sodium hydroxide have been added, the solution is predominantly acidic due to the presence of hydrochloric acid. Because hydrochloric acid is a strong acid, it completely dissociates into hydrogen and chloride ions. In this region, the concentration of hydrogen ions is high and the pH is low. Adding small amounts of sodium hydroxide will slightly neutralize the hydrogen ions, but the pH does not change significantly because the solution is still dominated by the acidic species. Then, near the equivalence point, the concentration of hydrogen ions decreases significantly, leading to a more substantial increase in pH with each addition of sodium hydroxide. This is where the pH curve becomes steep, indicating a rapid change in pH. The equivalence point occurs when the moles of sodium hydroxide added equals the moles of hydrochloric acid originally present in the solution. For a strong acid, strong base titration, the equivalence point is going to be at a pH equal to 7, resulting in a neutral solution because the products are water and a salt, sodium chloride specifically, both of which do not affect the pH. Then beyond the equivalence point, the solution becomes basic as excess sodium hydroxide is added. The additional hydroxide ions increase the pH, but the rate of change in pH slows down as the solution becomes more uniformly basic. In this region, adding more sodium hydroxide does not significantly alter the pH because the solution already contains a high concentration of hydroxide ions. So again, the equivalence point for a strong acid with a strong base solution is going to be at a pH equal to 7. Let's cover a strong acid with a weak base next. At the beginning of the titration, the solution is predominantly basic due to the presence of the weak base. Let's say ammonia. Ammonia is a weak base that partially dissociates in water. So in this region, when we're adding just small amounts of hydrochloric acid, the pH will not change drastically because the solution is still dominated by the basic species. But as more hydrochloric acid is added, the ammonia is gradually converted to its conjugate acid, ammonium. Then near the equivalence point, the amount of hydrochloric acid added is nearly enough to completely neutralize the ammonia. And here the pH curve becomes steeper as the solution transitions from basic to acidic. The equivalence point occurs when the moles of hydrochloric acid added equals the moles of ammonia initially present. For a strong acid, weak base titration, the equivalence point is going to be below pH 7 because the product of the reaction is the conjugate acid ammonium, which is slightly acidic. Now let's talk about weak acid and strong base. At the beginning of the titration, the solution is predominantly acidic due to the presence of a weak acid. Let's say, for example, hypochlorous acid. Because this is a weak acid, it only partially dissociates in water, resulting in a relatively low concentration of hydrogen ions. In this region, adding small amounts of sodium hydroxide, which is a strong base, will neutralize some of the hydrogen ions, but the pH does not change drastically yet because the solution is still dominated by the weak acid and its conjugate base. But of course, as more sodium hydroxide is added, the weak acid is gradually converted to its conjugate base. Near the equivalence point, the amount of sodium hydroxide added is nearly enough to completely neutralize the weak acid. The concentration of hydrogen ions decreases significantly, leading to a more substantial increase in pH with the addition of sodium hydroxide. The pH curve becomes steeper as the solution transitions from acidic to basic. Now, the equivalence point occurs when the moles of sodium hydroxide added equals the moles of hypochlorous acid initially present. For a weak acid strong base titration, the equivalence point is slightly above the pH equal to 7. So it's a little bit above pH 7 because the product of the reaction is the conjugate base, which is slightly basic. Now, our last category is weak acid and weak base. The equivalence point in a weak acid, weak base titration is particularly challenging to identify. So unlike other titrations that we've seen, The pH at the equivalence point for a weak acid with a weak base is not fixed, and it can really vary depending on the specific acid and base involved. It may be above or below pH 7, depending on the relative strengths of the weak acid and weak base. In general, weak acid, weak base titrations are not very accurate, and therefore they're rarely performed. With that being said, let's summarize. We have strong acid, strong base titrations. The pH is equal to 7 at the equivalence point. For weak acid, strong base titrations, the pH is greater than 7 at the equivalence point. And for a strong acid, weak base titration, the pH is less than 7 at the equivalence point. With that, let's go ahead and talk about polyvalent acids and bases. Titrations involving polyvalent or polyprotic acids and bases can be more complex than those involving monoprotic species. Polyvalent acids and bases, also known as polyprotic acids and bases, have the capability to donate or accept more than one proton or hydroxide ion per molecule. And this property leads to multiple stages of ionization, each with its own equivalence point, as shown in this titration curve here. Polyvalent acids and bases exhibit multiple equivalence points during titration, and each equivalence point corresponds to the donation or acceptance of one proton or hydroxide ion. This results in distinct stages on the pH curve, with each stage representing a different ionization step. For each proton that can be donated or accepted, in the cases of bases, there will be a buffer region on the titration curve. In these buffer regions, the pH will change relatively slow with the addition of titrant because of the presence of a weak acid and its conjugate base, or vice versa. Now, the pH curve for a polyvalent acid or base shows multiple stages, again, each stage indicating the successive removal or addition of protons. And this curve typically starts at a low pH for acids or a high pH for bases, and it changes gradually with distinct jumps at the equivalence point. Each proton in a polyprotic acid has its own pKa value, and the differences in these values often leads to distinctively separate buffer regions and equivalence points in the titration curve. With that, let's tackle a practice problem before we wrap up the chapter. This problem says, consider the titration of 25 milliliters of 0.08 molar sodium hydroxide with 0.1 molar perchloric acid. What is the pH of the solution after the addition of 15 milliliters of perchloric acid? Now, whenever you're solving titration problems, do not try to memorize an algorithm that might not work in every case. Instead, we really want to focus on the chemistry. In other words, you should write the net ionic equation for the reaction that is occurring. This titration involves the reaction between a strong base, sodium hydroxide, and a strong acid, which is perchloric acid. We've learned that the cations of strong bases and the anions of strong acids are always spectator ions in acid-base reactions. Therefore, we can actually ignore sodium and the chlorate ion, and the net ionic equation for the reaction of a strong acid and strong base is just hydronium ions plus hydroxide ions. They combine to form two water molecules. If a strong acid or a strong base or both are present on the reactant side, then the reaction goes to completion. It's why we wrote this one-way arrow. That means that this is a stoichiometry problem, and we should use a BCA table for this problem. Now remember, BCA table, we're working with moles or millimoles, so we want to make sure that we have that value to plug into the BCA table. This requires us to take the information we're given, which is the molarity and the volume, and try to calculate moles or millimoles. Here we're given the molarity and the volume in milliliters. So that means we can calculate the number of millimoles for hydronium ions, and we can do the same for the hydroxide ions. Now, for the hydronium ions, our concentration is 0.1 molar for the perchloric acid, and this is going to be multiplied by the volume, which is 15 milliliters. This gives us 1.5 millimole for the hydronium ions. What about for the hydroxide ions? Our concentration is 0.08 molar, and our volume is 25 milliliters, and this gives us an answer of 2 millimoles. Now that we have that, we can go ahead and set up our BCA table. Now, BCA, B stands for before reaction, C for change, A for after reaction. We just calculated that we have 1.5 millimoles of hydronium ions and 2 millimoles of our hydroxide ions. Now, for our reactants here, we have a 1-to-1 ratio, so the limiting reagent is going to be the one that has less millimoles, which is our hydronium ions. We're going to react all of our hydronium ions with our hydroxide ions to form water. All right, so we're going to be forming water. Now, for our after reaction, 1.5 minus 1.5, that's equal to 0. So we're left with 0 hydronium ions, but we're left with 0.5 millimoles of hydroxide ions. So this is going to be important because this after line is going to help us determine the pH. After the acid-base reaction occurs, we have 0.5 millimoles of hydroxide ions that remain. Now we can divide this by the total volume of the solution. That's going to give us the concentration of hydroxide ions. From that, we can get pOH, and then we can get pH. So let's go ahead, take this value, 0.5 millimoles. We're going to divide it by the total volume in milliliters, which is just 15 plus 25. It's just going to be 15 plus 25, and that is equal to 40 milliliters. And 0.5 millimoles divided by 40 milliliters, this is going to give us a concentration of 0.0125 molar. Okay, we're going to be using this value now to calculate the pOH, because remember, pOH is negative log of our hydroxide ion concentration. So we're going to write that down. pOH is equal to the negative log of our hydroxide ion concentration, which we just calculated to be equal to 0.0125. If we plug this into a calculator, we're going to get that the pOH is equal to 1.90. From here, we can calculate pH. pH is simply 14 minus the pOH. So 14 minus 1.9, this gives us a pH of 12.10. So what is the pH of the solution? After the addition of 15 milliliters of perchloric acid, the pH is equal to 12.1. Let's try to solve part B of this problem. Part B says how much perchloric acid must be added to reach the equivalence point. At the equivalence point, the number of millimoles of perchloric acid added must equal the number of millimoles of sodium hydroxide with which we begin. We already calculated that in part A. We said we have 2 millimoles of hydroxide ions. So at the equivalence point, the number of millimoles of hydroxide ions is going to be equal to the number of millimoles of hydronium ions. If we have 2 millimoles of hydroxide ions, we need 2 millimoles of hydronium ions at the equivalence point to reach the equivalence point. Then we can determine the volume of perchloric acid that's required to reach the equivalence point from the molarity and number of millimoles. We know that molarity is equal to number of millimoles divided by the number of milliliters. We have the molarity, we have the number of millimoles, we can go ahead and determine the number of milliliters by rearranging this equation. This gives us that the number of milliliters is equal to the number of millimoles divided by molarity. This is going to be equal to 2 millimoles divided by 0.1 molar. And this gives us our number of milliliters. It's going to be equal to 20 milliliters. So how much perchloric acid do we have to add to reach the equivalence point? We're going to need 20 milliliters. And with that, we've completed this chapter. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.